SwayamPrabha. Digital India. Educated India.
Good morning. Welcome to this course on transition and turbulence AE625. You can get my name and affiliation contacts given here. I would prefer that you can come anytime that you wish to, and just give me a phone call and just walk in. The title itself would suggest that we are looking at fluid flow transition, the instabilities that lead the flow to turbulent state. That is what is the main theme of this course. As we begin today, let me try to tell you a little bit about the scope of the course, the contents. We will start off with the introduction on instability and transition. That is what we will begin today itself. We need to really look at how the way the subject has developed over the period. It was quite early on understood that actual fluid flow behavior depends on flow instability. That means what? That you have governing equations of motions, and those equations of motions are most of the time nonlinear partial differential equations, are not solvable. In some specific cases you could solve them, and once you solve them, you would notice that you get some analytic solution, and you go to the lab, perform the experiment, and you do not see them. That is exactly what happened to Stokes. Sir G. Stokes, who is associated with the development of Navier-Stokes equation. So, he solved flow past inside a pipe and tried to compare his analytical solution with experimental data, and he did not find anything. So, it does mean that not all solutions are observable, we can see them. So, this is one thing that has really triggered the attention of many people. So, that is what we want to study in instability in fluid mechanics, because this is related to the instability of the solutions. What is instability? That if I have a solution, or if I have a physical scenario, then if I also have some background disturbances, which is not in my control, they do affect, and instability implies those small imperceptible disturbances to create large effects. That is what we mean by instability. Small cause leads to large disturbances, and there are classical theories developed, and you would be quite amazed if you have not heard of it before, that it was one of the pioneer in physics who actually picked this problem up to solve, and he is no other than Heisenberg. As a student of Sommerfeld, he first started looking at flow instability, and subsequently the German school led by Professor Prandtl and his students actually started looking at it. Two notable students are Tolman and Schlichting. Those of you have seen the book by Schlichting. So, this is the same gentleman. They worked on it, and what they found that the flow becomes unstable, and then you also see some waves. So, this is what we mean by Heisenberg, Tolman, Schlichting waves that we have written there. We'll be spending quite a bit of time talking about that. What is important to realize that again those theoretical prediction of instability theories are not to be seen in experiment. So, you can see that as a engineer by training or as a scientist by training, you cannot compartmentalize your activity. You cannot just simply say I am a theoretician, I do not know, I do not care about experiments. The same way experimentalist cannot make the same claim that we do experiments, if we do not see it, then your theory is wrong. This happens all the time, it is unfortunate business. And to tell you in this context also similar thing happened. When this 3 people one after the other started predicting these waves, it was nobody else other than Professor G.I. Taylor of Cambridge. He tried to experiment, and when he tried to perform those experiments, he did not see those waves. And so, that led to a sort of a very big debate, international debate. The German school is saying that there are waves, and the English school led by J. I. Taylor says there are no waves. So, what happens? That is what is a big story. Then came into the picture is this group from USA, Dryden and his colleagues. 2 of his colleagues, Schubauer and Skramstad, did perform some classic experiments at National Bureau of Standard in Washington. They did those experiments and they were the first to observe those waves. And to perform those experiments, they had to work very hard. They realized that not all kinds of disturbances give rise to waves. So, as a mathematician always you would see like people talk about flow instability in terms of eigenvalue problem. So, eigenvalue problem is what? You have a homogeneous equation, homogeneous boundary condition, and you try to get a solution out of it, and those are your eigen solutions. So, what does it mean actually? It means as if something is falling from the heaven. You are not putting any effort and you are seeing some results, right. So, that is another drawback of eigenvalue analysis. What one should instead look at is connect the cause with the effect. So, cause will be those background disturbances. They may not be always measurable, but they still would have some quality, and that is what Schubauer and Skramstad found out. Schubauer and Skramstad noted that not all disturbances produce waves. They could produce waves only when they vibrated a ribbon inside the boundary layer. They found out that if you try to excite the flow with acoustic noise, it does not create waves. And that is the subject that we talk about in this, what we call as receptivity, that the flow is receptive to certain class of disturbances. Not all disturbances can give you instability waves. Okay. So, if we are going to do that, we need to actually, instead of studying stability, we should be studying receptivity, and that is a major thrust in this course, perhaps unique in all over the world, that this subject is addressed in that framework. We do it here. So, we will be talking about receptivity, and what we would also notice that this experiment that was done by Schubauer and Skramstad required extreme care in setting this experiment up. You have to create virtually a noise free background, reduce the disturbance as far as possible. So, they actually designed a very nice wind tunnel. That wind tunnel even 70 years afterwards continued to be used somewhere in some US universities. So, you have to design a wind tunnel. You would find that there would be many experimental facilities, they make unsubstantiated claim that we have a very noise free tunnel, but they have no measurement of noise though. Well, we will not talk about that. What we are going to talk about is the reality, not the virtual one where people make tall claims. You really have to design a tunnel where background disturbances have brought down to 0, and then only you have to excite the flow deterministically, like as I told you in Schubauer-Skramstad experiment, that inside the boundary layer you started vibrating a ribbon. What happens if the amplitude of that vibration becomes very large? You do not see those waves. You do not see those waves. So, what happens is any transition, any instability and transition that takes the flow from a laminar state to turbulent state without showing the waves have been historically called in the literature as bypass transition. So, it bypasses the route of that Heisenberg, Tolman, Schlichting waves, right. This is what we would be studying. Then people also have realized that there are a large number of cases where your stability analysis shows the flow to be unstable, but in reality those flow also become turbulent. There are no flows which remain laminar forever. So, please do understand that laminar flow is an exception, turbulent flow is the rule. Okay. Unfortunately, bias in all the programs is to pretend as if laminar flow is everything and turbulent flow is a specialization. It is not true. People should know turbulent flow more than they should know about laminar flows, but to even to know how the turbulent state appears, you need to know this process of transition from laminar to turbulent. That is precisely what we are doing in this course, right. What happens is, as I told you, that there are many flow situations where you would not see these waves, it is bypassed, etc. And there are also cases where the instability theory even says that it would not become unstable, and nothing more to exemplify this is the case of a, let us say, pipe flow. Theoretically, it is shown to be stable, but we all know that a Reynolds number above 2000 based on diameter of the pipe, flow becomes turbulent. Then there is a squared flow, shear driven, right. If I have flow between two parallel plates and the top plate is moving, that is what we call as a quad flow. Quad flow is also theoretically found to be stable, right. However, those flows are not really stable. So, people have tried to study, one of the mechanism people talk about is some kind of spatio-temporal instabilities that may be affecting some of these flows, and this is what we are trying to look at. Okay. This is about wall bounded flows, external flows that we have been talking about, because most of us have a background of aerospace engineering. So, we are more interested in external flows, but then we also at times have to worry about not streamlined shape, we have to worry about bluff shape. Think of an aircraft when the landing gear comes out, that is a flow past a cylinder, right. Well, there are many such occasions, you would see there are cavities, etc. So, there what happens is we do not have streamlined body flows, instead we have bluff body flows, and they also suffer some kind of an instability. Okay. Now, instability per se can also occur in two different ways or a combination of these two ways. What are these two ways? The disturbances can grow in space, disturbances can grow in time, and disturbance can also grow in space and time. That is what we talked about, spatio-temporal instability, disturbances which simultaneously grow in space and time. Now, this earlier part, external flows that we talked about past streamlined bodies, one of the characteristic feature people have noticed over the years is that there the disturbances actually convect as they grow. That means, it is a spatial growth in space. Okay. In contrast to that, let us say flow past a cylinder is looked at, a bluff body flow, there you notice that initially the disturbances grow in time. If you are positioned in the wake, you will look at it, you will see it grows in time. Now, it is an interesting thing that that's basically a sort of a evidence of instability. The disturbances are growing, but nonlinearity plays a very different role for this external flows, or past a streamlined body and a blob body. For a streamlined body, what happens? The nonlinearity actually accentuates, increases the instability. That is where you go. Please do not understand, make this misconception that flow becomes unstable and boom, it becomes turbulent. It does not happen that way. The instabilities grow, then that disturbed flow further can become unstable. So, the first instability we will call it as a primary instability, the subsequent ones we will call it as secondary instability, tertiary instability, and so on and so forth. So, for a streamlined body flows, the primary instabilities are predicted very nicely by those classical theories, while the secondary and the tertiary instabilities are due to some kind of nonlinear effects, and they actually accentuate the instability. While for a flow past a blob body, we will show that the primary instability is a temporal instability, and nonlinearity here plays a very interesting role. Nonlinearity here actually moderates the primary instability. So, the waves keeps growing, but then it saturates. Okay, we will see this, we will spend a lot of time doing this. So, these are some of the interesting things that we would be talking about, and you have heard of Landau. Landau came out with a equation which is called Stewart-Landau equation, that tells you how this primary instability saturates into a nonlinear action into another almost neutral amplified waves. So, you start off from one equilibrium state, that was your laminar flow, it became unstable because of temporal instability, the nonlinearity saturates it. So, you actually get a time periodic flow. This is what you see as the vortex shedding behind a cylinder. That is a classic example, that you have a vortex shedding, Karman Bernard vortex shedding behind a cylinder. You say that they are very periodic, they do not just simply explode. That happens due to this nonlinear action, and Landau actually worked out the equation for it. And we will also talk about bifurcation. What is bifurcation? Now, we are talking about instability of flows. As I told you, flow inside a pipe, the classical linear theory says it is stable, but if I perform experiment, I find that flow cannot be kept easily laminar if the Reynolds number is above 2000. If it is above 2000, then you will have to make some effort, additional effort to keep the flow laminar. But if your Reynolds numbers are less than 2000, then even if you create a lot of disturbance in that flow, it still remains laminar. So, it seems the Reynolds number works like a kind of a parameter for the problem, and you have a critical value below which it remains stable, above which it is unstable. So, this kind of a scenario where actually we may look at let us say flow past a cylinder. If I were to be talking about on this axis, I will be plotting say Reynolds number based on the diameter, and on this side let me just simply plot the amplitude. So, basically what we are talking about that we are going to get some disturbances. Okay. So, this let me write it as u d subscript d implying disturbance field, and that I will write it as some A of t. I told you it suffers from a temporal instability. So, let us call that as A of t, and that would be multiplied by some function of space f of x, right. Now, this is that A that we are plotting, the time dependent thing. What we find that up to some Reynolds number, that up to that the flow remains laminar. That means what? This amplitude does not vary. So, even if you create some disturbance, that disturbance will eventually decay. So, this is something like your equilibrium flow. Okay. What do we mean by this? So, what we can do is, if I plot A of t versus t, I may get something like this, that initially let us say I create some kind of a disturbance, and if I am below this Re critical value, then what will happen? It may just simply go and decay. That is subcritical flow, right. So, this is the subcritical part, okay, and this part I will call it as supercritical. So, this is your a subcritical solution, where you may have initially created some disturbances at t equal to 0, but eventually decays. Whereas, in case of a supercritical case, what happens is something different happens. There what we will find, that suppose I start off with some virtually no disturbance at all, but there are background disturbances in the experimental facility. Then what will happen, for a supercritical scenario, I would have something like this. I will show you detailed results of this, theoretical, computational as well as experimental. People have done it, and they really find that something very interesting thing happen. It remains virtually like this. Then you actually see some kind of a very high frequency oscillations once in a while, and then it slowly picks up. So, this is what we meant by blob body flow instability, and then what happens is it just saturates to in an envelope, and this growth of the amplitude curve is what is of interest. So, in the supercritical case, what happens is you are going to see that starting from Re critical, this is your equilibrium state. So, this is my AE that we are talking about. This is that AE, the amplitude, it is 2 times, right. It is a periodic oscillation. So, it is 2 times AE. So, I can plot that, and what you would find that the scenario is like this, that up to Re critical, that equilibrium amplitude remains 0, and then it actually goes like this. So, this behavior is typical of blob body flows, and this transition from a subcritical to supercritical state is what is often called as bifurcation. Now, why do we call the solution bifurcation? It means that in the supercritical stage, I can actually get a solution which could be here, or if I am carefully doing the experiment, I can also have this case. For example, for the pipe flow experiment, we will talk about today itself, time permitting. Osborne Reynolds did those experiments. We talked about just now a Reynolds number of 2000 being the critical Reynolds number. Osborne Reynolds number carefully did those experiments, and he could keep the flow laminar all the way up to 12,830. Okay. Nothing to be surprised about, because later on people even did experiments and created pipe flow which were stable for a Reynolds number 100,000. So, what it means that your solution bifurcates from this point onwards. Here you will only have one solution, but here you will have multiplicity of solutions. Okay. Well, this is a very typical attribute of systems which suffer temporal instabilities, especially flow past blob bodies. You can think about it. So, this kind of bifurcation is what is called as a Hop bifurcation. Well, there are many types of bifurcation. Hop bifurcation is one of it. So, we'll use that, and we'll also talk about other interesting things like effect of heat transfer around flow instabilities. This is a very important issue, because if we are talking about, let us say, flow past flow in our atmosphere, the weather system. Here what you have? You cannot just simply talk about the instability of the atmosphere only in the absence of heat transfer. The heat transfer as it occurs, sun is our main source of energy, but these days we are also creating a lot of heat ourselves, right, anthropogenic heat transfer, right, man-made heat. How does it affect the system dynamics? You got to understand that in this course we are going to take a very deterministic approach of systems in studying their instability. So, what we are going to talk about is basically a system which I would represent by a, let us say, a black box. So, this is your system, right. Now, what happens to the system? The system is bombarded by input. We like it or not, they are there. That is what we have been studying, right, and then we get an output. And we have already seen the talking about receptivity is basically trying to connect input with the output through the system dynamics. What is the system dynamics? Okay. For the time being, I will call that as the transfer function. So, what does this system do? It takes the input, multiplies it by the transfer function to give you an output. Transfer function is then the property of the system. So, I can have flow in the weather system without the heat transfer. I am talking about one kind of transfer function. The moment I add the heat transfer, the transfer function has changed. This is what I was telling you also about Reynolds experiment. He did something to change the transfer function, or he did something to reduce the input, right. So, there are lots of very interesting thing in studying any dynamical system. This is basically is one of the goal of this course, that we talk about systems in nature as a dynamical system. Talk about the economics of a country, it is a dynamical system, right. We do not know how to model it, we cannot get its transfer function correctly, that is a different issue, but hopefully in future we should be able to do that. Look at all those smart Alex in the finance field, they actually play around, find out how those micro fluctuations in the input and they convert it into dollars in their pocket, right. That is also they study, they use chaos dynamics, right. So, we talk about this. Any practical system tells you that this transfer function need not always be very deterministic. A very good example is, as I always am fond of quoting, is tossing a coin. We cannot even predict its transfer function. Why? Well, I mean that is a part philosophic, part physical, but the fact is we do not know what are the players that determine the outcome, right. The same way economics as a subject, we do not know, there are too many contributing factors that makes the study of that dynamical system very, very difficult. You cannot get a deterministic portrait of it. We have to talk about it as a stochastic system, and that happens. This stochastic system means what? It is probabilistic, but also time dependent. That is stochastic, right. Tossing a coin could be a probabilistic event, but we do not know whether it is stochastic or not, because if I am doing the experiment in this room tossing a coin, depending on how the temperature inside the room is changing with time, etc., or if I keep a windows open or something and the air drifts in, that can all affect the outcome of the experiment. So, whether it is simple probabilistic time independent or it is time dependent, that is stochastic, we do not know. So, basically in terms of instabilities as affected by heat transfer is a worthy subject that gives us some glimpse of what may happen to a complex system. We will be talking about that, and then I will talk about secondary and three dimensional instabilities back to our aerospace applications, where we will see how this secondary and the three dimensional instabilities come into play. And I told you very clearly about this aspect, instabilities and transition. Instability does not mean that you would get a transition immediately, right. So, basically instability and transition are not synonymous. You have a finite region over which the flow becomes unstable. So, if I am studying a flow past aerofoil, so the flow can become critical at this stage, but if I am looking at say fully turbulent state, it may have happened here. So, this is what I may call as the critical point, and this is where let us say finally the transition takes place. Well, there are various definitions of transition quantifiable. So, let us say we adopt one of those and that says it is there. So, this is a very non-trivial space. So, this is what we will be calling it as the transitional flow. So, on this side we have laminar flow, and on this side we have turbulent flow, and these two are bridged by transitional flow, right. So, it so happens that this region over which transition occurs is not trivial. A very good example would be a flow in a turbine, in a gas turbine. You know, in a turbine flow accelerates. Accelerate means it is under the influence of favorable pressure gradient, while that turbine also sits downstream of the combustion chamber, and combustion through all those chemical reaction makes the flow very, very dirty, very, very noisy. So, you have a competing dialogue going on. You have a dirty flow coming in bombarding, and you are imposing a acceleration which is trying to moderate. That makes this region very, very significantly large. So, to understand transitional flow is a very, very important issue, and that is what we need to really keep aware of. And once you come to the turbulent state, you need to know what is really turbulent flow. And I would, time permitting, I will talk about this morphology, what constitutes. In this course, we are not doing turbulence modeling. I mean, we would keep that aside. We'll focus on the scientific aspect of it. We'll talk about it. See, basically all we want to do eventually try to understand what is turbulent flow. So, we have taken a different route now to in understanding this. We are coming from the laminar flow side and see where we are. Our point of view is that the turbulent state where we arrive would be determined by the process of transition. It is not unique. Okay, now we have seen what our course of content is going to be like. This is something you must be also curious to know what are the references that we are going to use. Well, we are going to use this book. This is a book that myself and Dr. Poinsot have written. We will not do the chemical reaction part, we will just do this part, instability of flows with and without heat transfer, right. So, this book is available. Apart from that book, I would recommend that one looks at this book by Drazen and Reed. It is now quite a classic book titled Hydrodynamic Stability, and this too will be more than adequate. There are many other books, you can take a look at them, but it is not necessary. Okay. So, we will stick to these two books only, and that should be adequate. And in the turbulent flow part, we have a very nice book here, First Course in Turbulence by Tenekis and Lumley. That is one book that we would be using in bits and pieces. But for understanding the morphology of turbulent flow, we would also be looking at this applied analysis of the Navier-Stokes equation by Dwering and Gibbon. This is a very short monograph, but very nice book, And as we seen and discussed that we like to study the flow as a dynamical system, and we try to find out what its transfer function etcetera is. So, that is covered very nicely in this book called Turbulence, Coherent Structure, Dynamical Systems and Symmetry. Philip Holmes and Lumley and Barkus, they have written this exceedingly nice book. Our interest is to basically characterize turbulent flow by some diagnostic tools of dynamical system theory. One of the dynamical system theory tool that we are going to use time and again is proper orthogonal decomposition. Let me tell you the good news that that tool was developed by Professor D.D. Kosambi of India. Despite all the things that you read in literature, it was Professor Kosambi who did that, published in a paper Indian Journal in 1943. Karhun and Loew and all other people came later. So, there is something we are going to use the POD as a tool, proper orthogonal decomposition, in trying to understand. You see, turbulent flow may look chaotic, but still within that chaos also you still would see some pattern, right. Those patterns are what are called as coherent structure. So, this was what was attempted. So, POD as a tool allows you to project that stochastic system into a deterministic basis and see whether you can pick up those coherent structure or not. That is what we are going to spend quite a bit of time. In fact, many of the students who work with us, with me, they do use POD as a tool, and we have done some very interesting thing in recent years using POD. So, we will do that. And there is also this book by Professor Davidson titled Turbulence. It is a fairly recent book, and you would find it interesting. Okay. This is something that would be of interest to you, that we will only have one midsem. Okay. We will have a comprehensive endsem which will cover the whole course, and I will ask you to do a bit of a term project etcetera. That would be 25%, and the smaller home assignments, your regularity etcetera will take care of this rest 10%. Okay. So, we will be following this, and this is the way that we would be doing. Now, this we already have started, we have told you, but still nonetheless we see how the subject of transition have developed over the years. Now, I told you about Reynolds experiment, but it was not Reynolds who started this investigation. Rather, I mentioned to you about those pipe flow means calculations done by Stokes and his inability to see those experiments, experimental values obtained by his theoretical analysis. What was the anomaly? Simply Stokes was looking at his laminar flow calculations, while the experimental results for the pipe flows, they are for turbulent flows. People were thinking, what is happening? I mean, what is this turbulent state? So, that really set into motion a lot of work that is embedded in work of Kelvin, Rayleigh, etc. They understood that instabilities are due to growth of disturbances. That is very fine. I mean, that is what we are all talking about, but they make a cardinal mistake. They said it is an inviscid mechanism. Rayleigh even found out an equation to show how an inviscid mechanism comes about. He gave some theorems and criteria to find out when flow becomes unstable. Now, they also made this observation that why one should look at the inviscid mechanism. Their point of view was very simply this, that if viscous action is there, it is dissipative, right. So, if there is some kind of a dissipative mechanism, that will actually damp out those disturbances. So, it is perfectly all right for us to study the inviscid mechanism, because if there are any viscous actions, they will only attenuate disturbances. This looks very convincing, compelling to follow, right. But then there were other people, mathematicians and physicists, who were not thoroughly convinced. Two of them, a mathematician by name Orr and physicist named Sommerfeld, they actually wrote down the disturbance equations including the viscous action, and that equation is called the Orr-Sommerfeld equation. This Orr-Sommerfeld equation is a central piece today, but in those days nobody thought that that was necessary, because I told you that the viscous action only attenuates disturbance. So, there are absolutely no need for adding in complication through the viscous action, right. Despite that, Heisenberg, under the guidance of Sommerfeld, wrote his PhD dissertation, and he did try to say what could happen. That thesis was very unique. The examination committee looked at the thesis, they could not find any mistake, but they did not also believe it. And that is the story of how quantum mechanics came into being. Heisenberg, after his thesis, stopped working on fluid flow, and he went on to establish quantum mechanics. So, you understand that this subject has a very checkered history. While Sommerfeld was a brilliant researcher, 4 of his students received a Nobel Prize, he never got it, right. So, that is another story. Subsequently, also along the same time, around the same time, Ludwig Prandtl and his students also were interested in looking at this instability problem. And I told you about those experiments, those calculations done by Tolman and Schlichting. They did come out with some results, but those were again negated by G. I. Taylor's experiment in Cambridge. He never could find it out, because Taylor did not read those results, analytical results very carefully. They predicted wave for certain frequencies, and in the Taylor's experiment he used a sort of a bump, oscillating bump on a flat plate, but the bump was oscillating at a wrong frequency, low frequency. And believe me, in almost in 95 or 96, we explained really what happened in those Taylor's experiments. So, it took another 60 years to come out to the, it was done here by one of couple of our students. So, if you try to excite a flow at a lower frequency and you do not see it, do not kill the messenger, right. Unfortunately, everybody did. But then around the same time, Dryden and his group at National Bureau of Standards did those experiments that we already discussed. That Schubar-Skramstad experiments, they figured out that to investigate and obtain those waves, you will have to remove the background disturbances and then give some kind of a deterministic disturbances of finite amplitude. Then your dynamical system picture is quite nicely constructed, right. You have a very definitive input and you know the laminar flow, that is your transfer function, and you try to find out what is your output going to be, those disturbance growing. And that actually helped the subject tremendously, those classic experiments done by Schubar and Skramstad. So, this was really the defining moment, and despite what is written in any book and many book, I would always refer to it as Heisenberg-Tolman-Schlichting waves. So, I will call it as HTS waves, but you will find in most of the literature they talk about TS wave. We should give Heisenberg his credit. In fact, he was one of the pioneers in this field. Okay. They obtained all those waves using a linearized stability theory. They made some assumption of parallel flows. Despite that, they did predict those waves, and Schubar, Skramstad found those out in experiments. So, this was a glorious period. Okay. And I mentioned to you also that there were many flows, pipe flows, channel flows, square flows that did not explain the flow instability by the same linearized stability theory developed there. Okay. So, you know, we are happy to give excuses, right. So, people gave excuses that maybe these are the suspects, nonlinearity because it was a linear theory, or maybe some nonlinear mechanism is taking place. Then the flow was considered parallel in this theory. Parallel means what? The streamlines are parallel, but you know a boundary layer grows, so they do not remain parallel, right. So, that is that. Growth part is important, non-parallelism, and maybe there are other unknown mechanisms. Okay. So, even today a large number of us try to spend time finding out some new unknown mechanisms. Okay. So, there are lots of such activities that goes on, but it was realized. So, I think I will stop here and we will start from here in the next class.